Today I'm going to talk about geodesic deviation, and what that essentially means is how particles on adjacent geodesics move over time. Okay, and we have the following situation over here. We have a geodesic here. This is the first geodesic, and then there's an adjacent geodesic over here. Okay, and that's identified by x alpha, which is a 4-parameter coordinate, of course, because we live in 4-dimensional space as far as we know. And we have lambda as the affine parameter that goes in this direction, and we have s as a parameter that goes in that direction. So the first geodesic lives at x alpha lambda s, and the second geodesic, which is adjacent, lives at x alpha lambda comma s plus ds, so a little bit further away. And if there is a gravitational field, what will happen is that these test particles that run through that gravitational field will find that when they initially started parallel, after some time they are no longer parallel, they are further away. There's acceleration between the two particles. Okay? And the reason why that happens is because there is a gravitational field, and there's curvature in this gravitational field. And therefore the gravitational field at this point is not the same as the gravitational field at that point. It's slightly different. And because that's the case, you get acceleration, you get particles moving away from each other. They initially started parallel, but after some time you see that that's no longer the case. So if you start with a differential vector, which indicates the difference between this particle and this test particle at say t equals 0, sometime later along this affine parameter, you will see that the difference is actually bigger. Okay? If you have a free particle and there is a gravitational field, it will follow a geodesic. Okay? So this free particle will follow a geodesic here, and the next test particle will also follow a geodesic over there. So how do we mathematically express that? We can do it in the following way. We have a 4-factor x alpha, which is built up out of a time, an x, a y, and a c. Okay? So this is really 4 different numbers packed into a vector. It has an affine parameter lambda, which goes along the curve, the geodesic curve. So if lambda goes up, you go a little bit further on the geodesic curve. And there's another parameter s, which indicates the difference between the two adjacent geodesics. Okay? We have a u alpha vector, which is the speed of the particle, and that's usually indicated by the differentiation between x, the position, right, and the affine parameter. So it's a dx d lambda, like you usually define velocities. Then there is the differential vector y, which we're interested in, because based on this vector we're going to calculate what the variation over time when lambda is increasing will be, and this will be an indicator for the acceleration at some point. Okay, let's start with covariant differentiation over here. So this is the definition of a covariant derivative, where you take a vector y mu and you differentiate that into the direction of u. So you differentiate this vector into this direction. Okay? And the definition for that is essentially given here. You can work that out. For now I'm going to assume that this is known. This can be derived. It's not too hard, but I'm not going to do it today. But if people are interested, let me know in the comments. I can do a video on this. So you have, first of all, you have differentiation with respect to lambda and s. And then you have a second component, and this second component is responsible for the curvature. This captures the curvature, and this essentially captures the base vector variation when you go along the affine parameter. If you're in Euclidean space, your vectors and your base vectors usually don't change. So if you move a vector from point A to point B, the the vector doesn't change and the base vectors do not change either. As a consequence, the Christoffel symbols, or the connection coefficients, how they're also called, will be 0. That's not the case if you have a curved space-time. These numbers essentially tell you how much the base vectors rotate in this curved space-time. And you have to capture that. Why do you have to capture that? Because if you differentiate, if the base vectors also move and vary, and not just the coordinates of the vector, right, the components of the vector, then you have to capture that obviously, and you do that using covariant differentiation. Okay, so now we can calculate the differentiation, the covariant differentiation of y, this vector, in the direction of mu, and that gives you this. You can also say I'm going to differentiate in the direction of y the u vector. So that's the other way around, right? If you calculate that out according to the definition, you see that this is exactly the same as this. Even though the parameters are different here. So you have a beta here, which is a dummy variable, right? That's just an implicit summation that is used in Einstein summation. This is the Einstein summation convention. And also for the nu here. So you implicitly add those. So this is a whole bunch of summations you see here. Yeah, beta goes from 0 to 3, nu goes from 0 to 3 also. But since these are dummy variables, you can replace the beta here with a nu over here, for instance, right? And then you get nu beta over here. Now these connection coefficients in Riemannian curvature, in a Riemannian manifold, are actually symmetric. So in these indices. So B nu is the same as nu B, so therefore these two are identical, okay? And you can conclude that this holds. So if you covariantly differentiate y in the direction of mu, that's exactly the same as covariantly differentiating mu in the direction of y, or u in the direction of y, okay? We need this later. So now we are in a position to actually do a covariant acceleration of the separation vector. Again, we're interested in this separation because if you have two geodesic curves that are closely toward each other, and you start with test particles that are parallel, over time they will move away, and that's because of the curvature in space-time, okay? And since we have Riemannian curvature, it will move out and there will be an acceleration term, okay? So let's start with the covariant acceleration, and usually that's indicated by big D here. You know that it is covariant if you use big D. If you use small d, it's just normal differentiation. So the acceleration is essentially 2 times differentiating. So we already defined our first differentiation here with respect to y mu, and you do that again with the second one, okay? Now we're going to use the property that we derived before, that you can interchange y and mu, and you interchange them here, and that's all you do, okay? And that results in the second line. Now we're going to work out this with just using the product rule. So first you differentiate with respect to yb, you do that here, and copy the second term. Then you take this first term in front, and you differentiate with respect to u, okay, to the second term here, to this term. So toward the covariant differentiation of u. Okay, so we have that. And now we're going to use the rule, non-commutative rule of covariant differentiation. And you have this if you have curvature in the system. And what this really tells you is if you have, for instance, you have 2 approaches, right? You can say I'm starting with a vector here in x mu, for instance, and I'm going to differentiate first with respect to beta. So you differentiate with respect to beta, for instance, and then you differentiate with respect to alpha here, and you do the same, but here you do it the other way around. And then you come into this point, into this new point here, x mu, and this is usually lambda plus d lambda, a little bit further out, and s plus ds, okay? a little bit further out, and this is your point lambda s. Okay, so it's a little bit further out on the manifold, in this case a Riemannian manifold, and you first differentiate in this direction and then in this direction, and you get a result. You do the same, but now you're going to differentiate first in this direction and then in this direction, and you will find that the vector that you had here is rotated in a different way. If you do it like this, you might get a vector pointing that way. If you do it like that, you might get a vector pointing that way. The reason is because of the curvature of space-time, of this manifold, that you get these rotations. You don't have that in Euclidean space. In Euclidean space, if you can actually interchange. If you have a vector, or in this case a scalar, you differentiate it in x direction and then after that in another direction, right? That's exactly the same as when you do it around, the other way around. It doesn't matter, it's the same. In flat space-time that will be the same. That's not the case in curved space-time. So we use that to rewrite this portion here. So what states here is essentially b beta alpha minus alpha beta, okay, times mu mu, u mu, okay. So if you rewrite that out, you can rewrite this equation into this, or this equation here, which is essentially this term. You take that to the other side, and that's then exactly the same as this plus the Riemannian curvature over here, okay. Now you can say I'm going to work out this one. I'm going to pull u behind the first covariant differentiation over here. If you do that and you work it back out, you will get, okay, first I have to differentiate with respect to the first term, which is not there. Then I have to differentiate with respect to the second term and take this in front. That's the term that's standing here. So that first term you need to subtract from the result, otherwise you get too much, right? So that's what we did here. So we translated this term into these two, and we rewrote this one. Now if you look carefully, with this one and this one go away, because this one you can use the same trick as what you used here, exchanging the y's and the u's here, relabeling alphas and betas over here, and you will see that this term is exactly the same as this. Okay, so that falls away. This second term, what you do here is you differentiate, covariantly differentiate in the direction of u, your vector u. So what you do is you move in the direction of the geodesic, you move u over the geodesic, and you ask yourself, how is u varying when I move over u over the geodesic in the direction of u? Of course it's not varying, right? So this is 0. Okay, so what you're left with is essentially the Riemannian curvature and the three vectors here, right? U alpha, y beta, and u nu. And that's exactly your covariant acceleration here. So your covariant acceleration is really only due to the curvature of space-time, that if you have two particles that start parallel initially, moving parallelly close to each other in a gravitational field, a little bit later that will no longer be the case. And that's because of the curvature, the Riemannian curvature of space-time. And how does this Riemannian curvature come about? There might be a black hole, there might be a sun, there might be a moon, there might be the Earth, right? And because of those masses, you get curvature in space-time, and therefore you get geodesic deviation. Okay, I think this is a great place to stop. I hope you liked this video. It was somewhat technical this time. But if you like it, please subscribe and please like, and I'll see you in the next one.